so much, Mr. Chairman, and thank you everyone for bearing with us through the last afternoon of the session. The title of my talk is Plant Performance Improvements Using Classification System Efficiency, or CSE for short. And it's not advancing. There we go. This is a little bit of a story about discovery, and the topic of the discovery is the discovery I made about the ball mill circuit, ones that we all work with in our plants. And the premise of this presentation is that everyone can increase their ball mill circuit's efficiency and improve downstream plant performance, often very substantially, by the steps provided to maximize classification system efficiency, and as demonstrated by these 6 plant case studies. So by way of outline, I'll take you through the origin or the discovery of this term, classification system efficiency, how it's been used to increase grinding circuit efficiency and improve downstream plant performance through 6 examples. And these are chronological examples. The first one is the very first case study that we conducted to test and prove out this parameter. And the last couple are more recent, routine, step-by-step, systematic analyses that were carried out in recent times to improve classification system efficiency. And then, by way of summary and conclusions, what we've learned to date about classification system efficiency and how you can apply this tool in your milling circuit. Now, I have to go back to my own background. When I first graduated from McGill in 1973, I went to work for Allis-Chalmers Canada, and my job was a slurry pump application engineer. And I spent a couple of years learning from some of the best people in the business about how a slurry pump works and how to select it for a given application. I was then transferred to become a grinding mill application engineer, and this was the time that Fred Bond was still employed as a consultant with Allis-Chalmers, and I worked with Chet Rowland and a number of brilliant people in that area. I was very, very thoroughly trained in the ins and outs of grinding mill application engineering. And then, by pure coincidence, I was given an attractive job offer and moved to become the manager of process equipment at Linatex, specializing particularly in hydrocyclones. Linatex isn't known today as a major hydrocyclone supplier, but historically they were a major supplier and developer of hydrocyclones both throughout South Africa and Australia. And there was an immense amount of knowledge that I was given access to through the people at Linatex to learn about hydrocyclones. And of course, the grinding circuit is made up of the pump and the mill and the hydrocyclones. So I was given a tremendously valuable and unique opportunity to learn about this, each of these pieces of equipment. And as a result of that, which is pretty much just coincidence, I was able to make a pretty important discovery. I'll just go back. Having learned about pumps and cyclones and mills from all the experts, I was able at that time, back in before I went back to McGill to do graduate work, I was able to make changes to the cyclone and the pump to change the circulating load, to manipulate the water balance, and to do all those sorts of things. That's what we were taught to do as process application engineers with those pieces of equipment. One thing I always scratched my head over was this graph, which was published in the famous book by Godin in 1939, but which he refers back to work that was done by Professor Davis in 1925 at the Minnesota School of Mines Research Station, where he set up a pilot plant and manipulated the circulating load ratio in his grinding circuit from open circuit, that is no circulating load, up to a circulating load of 400, 500, 600%, and clearly demonstrated that the quantity of new product size material, new minus 150 mesh material, went from 100 to 2 to 260, 270 tons per hour with exactly the same amount of energy by implementing a higher and higher circulating load. And like many others, I'm sure I scratched my head over this for many, many years until I was looking at this one day, and I call this my Eureka slide. I was looking at two sets of data, and they weren't particularly good sets of data, but they're the ones that I had to work with in my job at Linatex from two different grinding circuits. These two different circuits had the same roughly F80 coming from a crushing plant or from a rod mill, and the same P80 going out to cyclone overflow. However, what was different about them, one had a high circulating load ratio, and these lines represent the size distributions in and out of the ball mill itself. The one with the low circulating load ratio had a much different set of size distributions going in and out of the ball mill than the one with the high circulating load ratio. And what I observed was, aha, with a high circulating load ratio, we've got something like, 85% of our material in the ball mill on average is coarser than the P80. That's the material that's getting the grinding energy. It's getting 85% of the grinding energy of our mill. Whereas with the much lower circulating load ratio, say 75%, only 75% of the material in the mill is coarser than the P80, and that's where 75% of our energy is going. And since I already knew previously how to manipulate and take this situation into this one, I had the ability to improve grinding efficiency. So having made this discovery, we took that evidence and I returned to McGill University where we built a ball mill circuit model, which was common at that time, and explored changing the circulating load in a simulation, in a computer simulation. What if we changed the circulating load, increased it from 160 to 500%? What would happen to the production rate of this circuit? And we started with an original set of data that came from Craigmont Mines in British Columbia that had a circulating load of 160%, was producing 203 tons an hour of new product. Okay, now this is looking at things a little bit different. This is the tons per hour of new product of minus product size. In this case, I think it was minus 150 mesh. And when we looked at that in the simulation, the mill contained 55 out of the 100 units of material of the holdup in the mill were coarser than the P80. When we increased the circulating load to 500% by playing with the simulation, the production rate went up by 29%, and the percentage of coarse material in the mill, coarser than the P80, went up by exactly the same ratio. In fact, if you looked into the math of the circuit model, that's all it was doing. It was saying we're putting energy on 71 units of material instead of 55, and therefore the production rate up. So we're able to make this simple, clear definition. The classification system efficiency is the percentage of coarse solids in the mill versus, and it's also equal to the percentage of the mill power being used to grind the coarse solids. So what we're looking at is what's going into the mill, what's coming out of the mill on average. What have we got inside this mill? If we've got 80% of our material in here and 1,000 kilowatts connected to it, then we're using 800 kilowatts to grind. If it's 500, then it's 500 kilowatts to grind. It's just that simple. So in approaching circuit analysis using classification system efficiency, and another way to think of this is just think of CS, coarse solids. That is solids in the mill that are coarser than the target, the P80. We define coarse materials as those that need to be ground further, and fines are already fine enough. They should be downstream in flotation or leaching. The circuit target P80 is typically a good way to do the analysis. So we usually say anything coarser than the P80 is coarse, anything finer is fine, and we do our analysis based on that. And increasing the mill power expended on coarse directly increases circuit grinding efficiency, directly and linearly. And simultaneously, it reduces the mill power expended on fines, which is reducing wasted energy, recapturing it and putting it back where it's useful, and also reducing overgrinding. And so we can say, for example, we can define effective mill power. That's our total mill power times our percent of coarse solids. The wasted or overgrinding mill power is the total minus that, or the total power times 100 minus that. So we're focusing on what is actually in this circuit in a steady state condition. This is all about steady state analysis. What is inside this ball mill under a given set of operating conditions, given the setup of the pump, and the cyclones, the water balance, and so on. And here's an example of how we calculate it. We take the average of the size distribution coarser than the feed and the discharge. For instance, if the P80 in this circuit is grinding to 80% passing 106 microns, we take the percent of coarse, the plus 106 microns in the feed, the cyclone underflow, the percent of course in the ball mill discharge, and we take the average. Okay, and in this case 76%, it's a little finer going out, the average is 71%. We can say that 71% of the material in this mill is coarser than the P80, and we are effectively using 71% of whatever amount of kilowatts we're putting into that ball mill. Now you can use a much more sophisticated or complex model to do that. If you were to use plug flow, you would see instead of 71, this would come out to 71.04. Or if you were to use a very complex model with residence time distribution, instead of 71, this would come out to 69.95. But for all intents and purposes, this is a very, very accurate model. And remember, what we're also interested in is the change, in the relative change in this number. Okay, so as an example, that first case study, at low circulating load, our coarse solids was 55%. The circuit was processing 100 tons an hour, and let's say the mill power at the pinion was 1,000 kilowatts. So our effective mill power was 55% of that, 550 kilowatts. The wasted overgrinding power was the rest, 450 kilowatts, or 450 divided by 100, we were wasting 4.5 kilowatt hours per ton on overgrinding. So if we increase the circulating load to 71%, the circuit efficiency increases by 1.29. Okay? And our tonnage is increased to 129. Our new effective mill power is 710 kilowatts, simply 71% instead of 51%. Our wasted overgrinding power is 29% of 1,000 kilowatts, or 290, but based on the new tonnage, it's 2.25 kilowatt hours per ton. So we reduced the amount of overgrinding of material that's already suitable size for flotation from 4.5 to 2.5 kilowatt hours per ton by the nature of the beast, a reduction of 50%, no small amount. And why do we want to do that? Well, of course, when we can produce a narrower size distribution, which is associated with things like a high circulating load in the circuit, versus a very flat size distribution going to flotation, which is associated with open circuit grinding or low circulating loads or poor classification system efficiency, we feed something much different to our flotation circuit, and this is just an example of many, many that we all know that the performance of a flotation circuit and many other mineral separation processes is very sensitive to particle size. And the more material we can squeeze between in the high recovery region, the overall increase in efficiency, the overall increase in metal recovery we're going to achieve. Okay, so that was the first case study. The second one was done at Kid Creek Mines during my time when I was doing my PhD work there. And they asked us a funny question. They said, this was a survey we did. And they said, we want to reduce the circulating load ratio. Well, why do you want to do that? Well, they didn't have enough maintenance crews to keep all their lines running, and they were literally experiencing significant downtime. They said, we want to drop the circulating load, but how much efficiency are we going to lose? Downstream performance wasn't an issue because this was the first stage of a two-stage ball milling circuit, so we assumed there would be no effect on flotation. So having done this survey, we modeled what would happen if we went to a lower circulating load and looked at going to 250 up to 550. We knew what happened in terms of relative circuit efficiency because the classification system efficiency at the target P80 changed like this in our circuit models. The relative efficiency actually went down 2% when we went to 350 from 450. But, and our milling costs, therefore, for energy and grinding media went up. But we were able to establish that our costs for pumping, including maintenance, would go down, and the net minimum operating cost of the circuit was actually at a circulating load of 350% rather than 450. So they went ahead and reduced the circulating load, took a little bit hit in grinding efficiency, and kept their circuits running. Okay? So this tells us, for one thing, that our optimums are not when the efficiency is at the maximum. All our optimization criteria are economic criteria. So this is the optimum economic circulating load at Kid Creek Mines. Okay, here's another example. We were looking at two circuits a couple hundred miles away from one another. This was at Salvé, where we measured the work index of efficiency of the circuit, compared the work index of the ore to the operating work index, and it came out to very close to 100%. So I used this circuit a lot, all the data from it to build models and so on. Down the street at Dome, in a gold processing plant, where they had this circuit, their work index efficiency was 134%. Bond says to do this amount of grinding, you need 13.4 kilowatt hours per ton. They weren't using 13.4, they were using 10. So why the difference? And you can see that they, at Dome, what they did is they took the primary cyclone underflow, it went into gravity gold separation. When it came back, there was a lot of water, so they put it through a second stage cyclone before they put it back in the mill to bring the density back up. And if we look at the percentage of coarse material, coarser than the P80 in either case, we're able to see that this difference in efficiency, circulating loads were fairly close to the same. It was a very favorable water balance at Dome, and about 2/3 of the advantage of the efficiency of Dome was explainable by the percentage of coarse material in the mill. And this was attributable primarily to the water balance, because when we modeled this and took out the two-stage cycloning, we only lost about 5%. So all the rest was due to the water balance, the fact that the Dome was producing a cyclone overflow of about 15% solids and sending it to a thickener. Here's an example of two plant experiments we did at Tilden some years ago, where we did a sampling of one of the pebble milling circuits, and one of the objectives there was to drive up circulating loads because we saw they were quite low. And the grind target is typically 80 to 90% passing 25 microns. So on the basis of 25 microns, we did a survey of the circuit, crash stopped it, came in and had the maintenance people put on new shivs on the pump, started it up again in order to try to get the exact same operating conditions except for one change in that circuit, the speed up of the pump. As a result of this, the circulating load went up, the cyclone overflow was more dilute, and we had an increase. If you take a ratio of those, we had a 4% increase in circuit throughput and in efficiency. And this is significant. All it's based on is a size distribution of what's going into the mill and coming out of the mill and taking the average. And the accuracy with which we could measure that told us we did indeed have an increase in grinding efficiency by doing that. A more recent example, the installation of high-efficiency cyclones, the new modern design, K-Maxes or G-Maxes, at a nickel concentrator in Sudbury, the Strathcona mill, where we did a baseline survey, and their CSE, or their coarse solids in the mill, based on 212 microns, which wasn't their 80% passing size, a little bit finer than that, but nevertheless chosen to be the reference point for the study. The objective was to evaluate replacing the old style cyclones with new modern high efficiency cyclones, and we could also allow the cyclone overflow percent solids to become slightly more dilute. Here's the survey, initial survey cyclone performance curve, and this is the reduced curve, and we did some test work with a new modern cyclone. Watch what happens up in this region. It's essentially the same D50C, and we got rid of a lot of coarse particles. The overall sharpness of separation improved significantly. So we took our model, replaced the old cyclone with the new cyclone, ran it, and predicted that we would get a 7.5% increase in productivity because of the increase in classification system efficiency, the reduction in the amount of material that's being, energy being wasted. The cyclone overflow size distribution also was noted to become significantly narrower. Overgrinding decreased by 16%, and the maximum particle size going to flotation went from about 1,600 microns down to about 800. Okay. So in addition to the improvement in grinding efficiency and the reduction in overgrinding, there was a significant reduction in the amount of coarse particles going to flotation. So if you don't have some fairly modern, new, high-efficiency cyclones in your plant, it's time to look at that. These were the predictions that were made. They installed the cyclones, and the results were essentially as predicted. Final study done for Barrick. The question was asked, we're having some difficulty at one of our plants. We're not getting the grind. We're not getting the gold recovery. What would happen if we could put a lot more water into our cyclone and improve the performance that way? So we started off, this was one of those cell-based surveys where we had a 42% solids in the cyclone overflow. That gave us a feed percent solids of that in the cyclone feed, selectivity, and so on. And this was our classification system efficiency, the percentage of coarse material at that condition. Based on that survey, we modeled what would happen if we had to increase the cyclone overflow percent solids to 50%, because that's what they were feeding CIL. That would actually drop the classification system efficiency down to 64%. In other words, we would lose 11%. But by putting more and more water into the cyclone, of course, this is a new cyclone selection and a new pump and so on, we went all the way down to 10% solids. We looked at what would happen to the classification system efficiency, and in this case we kept the P80 the same, we kept the tonnage the same, and we dropped the mill power. Okay? And if you multiply any pair of these numbers, 523 times 71%, or 430 times 86%, you get 370 kilowatts in every case. In other words, we're using 370 kilowatts. That's our effective mill grinding energy on the plus P80 particles in every case. It's just we're doing it more effectively because of our classification system. We saw a net overall increase from 50% solids in the cyclone overflow to feeding a thickener at 10 to 15%, approximately a 30% increase in circuit efficiency. And if we push the circulating load up a bit, these were all based on a 330% circulating load. We could, based on 20%, we could get a little bit more. So this was highly, highly significant in terms of how much the efficiency of the circuit could increase. Just note that if we look at the overgrinding energy, we went from 34% of 580 kilowatts to 14% of 430 kilowatts. That's a reduction in overgrinding of 70%. Okay. They moved the thickener into the process. They made some changes to the pumps and cyclones. Their grind got 6 to 11 points finer. Gold recovery went up a couple of points, and we were all pretty happy about that. So here's just a quick summary of those 6 case studies. There's at least 9 or 10 more I could go through with you. Some of them with successful outcomes in terms of significantly increasing the circuit and classification system efficiency. Some proved simply what we did had no benefit, always looking back at the classification system efficiency. The initial modeling study was not implemented at Craigmont because they were long out of business. And but the optimum economic circulating load at Kid Creek was successfully implemented. We diagnosed the higher grinding efficiency at Dome versus Sal Bay. We couldn't do this at Sal Bay because Sal Bay needed to feed their flotation 35 to 40% solid, so we couldn't drop it down there. The cyclone feed speed up at Tilden was successfully demonstrated and was starting to be implemented at the time I left there a few years back. The new high-efficiency cyclones at Strathcona, they were successfully implemented. The use of a thickener for more dilute cyclone overflow at Barrett to Tulawaga, again, successfully implemented. So the conclusions, when we look at this value, the percentage of coarse material in the mill, how do we achieve that? We achieve it by having a high circulating load ratio in our grinding circuit, 400 or 500% or higher. Maximum use of cyclone feed water, because of course that gives us the minimum bypass and fewer fines back to the mill. And a very good cyclone selectivity, like the new modern cyclones do. And capacity, because when they offer us more capacity, lower pressure drop, we can put more water into the circuit or run at a higher circulating load with the same pump. And of course, all these are closely tied by the cyclone feed pump motor capability. And you can go to the presentation I made here last year, Pump and Cyclone Design Optimization to Maximize Grinding Circuit Efficiency, a systematic method to see the steps that are used to change the setup of the pumps and cyclones, to make any of these changes, and exactly the same procedures are used to optimize existing circuits or to design new circuits. So how do you get started? Well, if you go out to your plant and do a quick survey where you take a sample of the overflow, a sample of the ball mill feed, and the ball mill discharge, you will be able to calculate your classification system efficiency at the P80. If this is 106 micron, and on average this is 70% coarser, your classification system efficiency is 70%. So take a set of those readings and then compare it to the database. Our database is in the paper. This is the database. What this shows is that, and conservatively, it's a conservative database because at 300% circulating load ratio with old style cyclones, with a cyclone overflow percent solids, depending on how you're constrained, either feeding CIL or in this range feeding flotation, or maybe in this range feeding a thickener, you should have a number in this range, 70 to 72% feeding flotation, and as high as 86%. This is kind of the wall. Okay, really high, hard to get it above that value, whatever you're doing. So you can compare it to that, and then you can see the procedure that's used which was presented here last year, or you can go through it with our online training program. So, by way of overall summary and conclusion, plant performance improvements. This is a powerful, simple metric to benchmark current circuit performance and to evaluate any or all grinding circuit classification options. Increasing circulating load ratio, water usage, cyclones design, type of classifier, screen, and so on. You can analyze any type of classification system with this. And all changes in circuit performance will stem from the change in the percentage of coarse material in the mill. Assisted systematic method for maximizing CSC is available. And as we increase CSC, it's very important that we are not only recapturing wasted overgrinding mill energy and putting it to proper use, we're also reducing overgrinding. And that means higher metal recovery downstream, easier filtering, increased backfill recovery, higher tailing settling rate, and so on. And with every new study application, we learn more. I had the good fortune to do a study in the plant just late last year, 960% circulating load ratio. The question was, does that curve, that Davis curve, keep going out and keep increasing all the way up to 960%? It does, even in a plant, not just in a lab or on a computer simulation. So it begs the question, where is your ball mill energy going, or what is your ball mill circuit CSC? And I'd like to certainly acknowledge the support of numerous mining companies who let us play with their toys, and McGill University for their ongoing support. Thank you very much.